And I'm going to talk today about how we work in the Boost community and how we try to evolve the APIs you find in the Boost libraries. So if you know me, you know that I've been giving a lot of talks about the Boost libraries at conferences before. This talk is a bit different today. So the goal of this talk is not to introduce you to a library in a way that you can use that library afterwards. This talk today is about the processes in the Boost community. How do we work in the Boost community? What kind of problems are we trying to solve? How do we try to solve the problems? And what kind of design decisions do we make when we work on Boost? I have now a new laptop. Okay. Oops, sorry. So when I think of the Boost libraries, I do not only think of the code in the libraries. I do not only think of the documentation we find on boost.org, things you probably are familiar with. I guess most of you have used the Boost libraries before. I think of a little bit more. So I'm standing here today as someone from the Boost community. So I think of the community behind the Boost libraries as a community of developers trying to establish existing practices. So when we work on Boost libraries, we are not just trying to create something useful, but we are trying to design the libraries in a way that we believe they could maybe be shipped with a C++ standard library one day. So we are really aiming for a very high standard. It doesn't always work, especially not when you are starting to work on the library for the very first time. It takes a couple of iterations until you get there, but that's what we are aiming at. So when you look at the Boost libraries and you want Boost libraries to use in your own projects, it is not about using something other people created before, stuff you can reuse. It also gives you an idea how developers in the Boost community think, what kind of design decisions they make, and how they approach problems. And I think it's a really important part because you can learn something from that very influential open source community in C++, just by looking at the Boost libraries. So I hope that this talk today gives you a little bit of an idea what we go through in the community when we work on that stuff. Boost is also a little bit of a recruitment program. The open source community has participated in the Google Summer of Code program for, I think, at least 10 years. I don't know whether you are familiar with the Google Summer of Code program. It's a program run by Google, where Google financially supports open source organizations and actually pays students to work during their summer internship on open source projects. And Boost was one of the open source organizations that always benefited from that program. We had a problem this year. This year, Google didn't select us, not because they don't like us anymore. They just want to make sure that other open source organizations get also the support from time to time they deserve. So they don't want to make sure that they don't want to spend the funds always on the same open source organizations. They, of course, also want to support other organizations. So I'm saying this because somebody else stepped in this year and decided to sponsor the Boost Summer of Code program. That is a company from Amsterdam called IMC. Disclaimer, I work for this company, so it's not a coincidence that they decided to support Boost in that regard. But I will come back to this later again as I talk about the Boost community here and all the things we do there. So far, maybe you were only a consumer, happy that you can use the Boost libraries, but we are also happy if you decide to step up and get active in the Boost community one way or the other. That does not only mean writing code, that can also mean stepping up as a sponsor and making sure that the guys in the Boost community can work on useful stuff. So during my talk, I will look at one specific library called Boost Process. You maybe have never heard about this library before. The library is around for a long time and hasn't been a Boost library up to more or less 2 weeks ago. So it's the latest addition to the Boost libraries. And what does Boost Process do? You would use that library if you want to create child processes, if you want to set up streams to communicate with child processes, if you want to wait for child processes to exit, if you want to terminate child processes. So every time you have a program and you want to start another program from within your program, you could use that library. That library is a library we have been working on for 10 years. So the first draft of this library was created in 2006. And you might wonder, what the heck did we guys do in the Boost community for 10 years that we can't write code that actually works? So that is a pretty difficult library to work on. It was very difficult to get it into Boost because there are a lot of goals we were trying to go after. And just to give you a quick idea of what these goals were, well, one of the goals is obvious. When we work on Boost libraries, we want, of course, the Boost libraries to be platform independent. That means for Boost Process, we want to support the library on Windows, on Linux, on Mac OS. And if you are familiar with these operating systems and the APIs they provide, then you know that obviously all these operating systems have processes, and you can create a child process from one process, but the APIs are very, very different. What we're also trying to do, we are trying to remain close to the underlying operating system concepts. So if you have platforms with very different APIs, well, one thing you could do, you could just come up with another concept on top of it and abstract everything away, what you find in the operating systems. But that would mean you are making a step towards something which looks more like Java, right? You are inventing something brand new and forget about all the underlying concepts. And that is something we don't want to do when we work on a C++ library and on a library in Boost. Okay. What we were also trying to do when working on Boost Process, we wanted to create a library which is extensible. There are a lot of things you can do on one platform, like on Linux, and there are other things you can do on another platform, like on Windows. And we want people using Boost Process to have the flexibility to use these platform-specific features. So we want to avoid that you start using Boost Process, and then you want to use a platform-specific feature, and you can't do this anymore. And you are kind of locked into the library, and your only choice is throwing the library away and rolling out your own code. What we, of course, also want to do, we want to allow you to write safe code. There should be no uncertainties, there should be no surprises, and of course, there should be no frustration. That sounds all pretty much abstract, but we are going to look at a lot of code, a lot of examples. So let's start with something really simple. If you want to create a child process today and you don't have access to a library like Boost Process, you could just use the function stud system from the C++ standard library. So here's a simple program. You want to see the contents of a directory. So you run the dir command, something usually supported on Linux and Windows, and you get the output of the dir command. You see the files and directories in the current directory where you run this application in. Now, where is the output written to? It is written to the text console where you execute this program in. Now, what if you want to get the output of the dir command and want to process this output within your C++ program? That is one of the use cases where you could turn to Boost Process, and you could write code which looks a little bit like this. I say a little bit because this is not necessarily code you could just copy and paste into your IDE and compile with Boost Process. As I said, the library Boost Process was added to the Boost libraries 2 weeks ago. There were a lot of comments in the reviews, so there are still some things being changed while this library enters the big repository of the Boost libraries. So it's not yet all really worked out, but this gives you an idea what you can do with that library. So here I want to execute, I want to run the dir command, and I want to capture the output. I want to process it in my program. So I came up here with a function called execute, and then I pass 2 named parameters to that function. One is called shell, the other one stood out. And shell I assign a dir string to, that is the command I want to execute on the shell. And what I do with stood out, I want to redirect the standard output stream of the child process to the pipe P. So whatever is written by the dir command to the standard output stream is actually written to that pipe, which I created in the first line with makePipe, another function from Boost Process. And then at the end of that little program, I read from that pipe. In this case, I read into a string stream, and from there on, I can continue and process the output of the dir command in my program. I guess something very simple. So if this is how we imagine how we would like to create a child process and capture the output of the child process, then we have to look at the execute function and think about how are we going to implement that function. So we know there is this system command in the standard library, but obviously that is something we cannot use because it doesn't allow us all these things we want to do in that program. So if we look at what we find in the implementation of execute in Boost process, then we see that we call system functions. So you don't need to read all this text. This is just to give you an idea how different the system functions are we find on Windows and Linux. So on Windows, we would call a function called create process, which I think accepts 10 different parameters. And on Linux, we would call actually two functions, fork and another function called execve. And fork doesn't accept any parameters. Execve wants 3. So if you think about how you could now design the execute function, your first idea could be, all right, we actually need to support 13 parameters, the 10 parameters on Windows, the 3 on Linux, and we are done. Unfortunately, it's not that simple. It turns out that you have more configuration options when you set up a child process than you can see here. For example, on Linux, when you want to create a child process and you want to set the root directory of the child process, you would call an additional function called change root. So through the function called change root, you would change the root directory of the child process. It's not a parameter which you pass to one of these functions here. It is yet another function you would call between fork and execve. So the question is, how are we going to support this in Boost process? I mean, it's nice if Boost process supports all these functions, but then one of the library users will ask us, okay, I want to change my root directory. How am I going to do this? Now we know, of course, that change root exists and that it is an option we could maybe support with execute by adding yet another parameter, but who knows how many functions there are developers would like to call between fork and execve. After all, change root is just one example of what you can do to set up the context of the child process. So how can we support arbitrary named parameters? So we have a couple of parameters we know we want to support. That is something the APIs on Windows and Linux support anyway. But it looks like that developers would want to set maybe way more configuration options, like change root. So how can we support this with a function like that? All right, let's just look at a couple of ideas. So what we could do, we could define execute like that. Execute accepts now a vector of pointers to a base class. So we don't pass the parameters anymore as named parameters like shell, comma, stood out, blah, blah, blah. We just pass a vector with pointers to a base class. That base class has a virtual destructor. Has a virtual destructor because we're going to derive a lot of classes from that one. Then we can add to that base class a couple of handlers like setup, create process, setup, fork, setup, execve. These handlers correspond to the functions we have just seen, which will be called later on the different operating systems to actually create a child process. Then we can also create two structures like create process params and execve params. So here the structures are empty because I was running out of space. But the idea is to put into the create process param structure 10 variables. All these parameters create process expects on Windows. And in the execve param structure, we would put 3 variables, namely the 3 parameters we have to pass on to execve. And then we can define our own classes, derive these classes from base arc, implement the setup handlers the way we like. So we could access these parameters because they are these structures pass by reference to our handlers. We can access these parameters. We can set up the structures the way we like. And when we look at how that implementation, how all of that would be used and execute, it would look a little bit like this. So somebody passes a vector with pointers to us. These pointers refer to objects based on classes all derived from that base class. And what we are going to do then, we are going to iterate over all these pointers in the vector. We are going to call the handlers on these objects. We are passing these structures so that the objects have a chance to modify the parameters which we will pass on later to the system functions. We are going to do this first with setup create process and setup fork. And then afterwards we call create process on Windows, and on Windows we are then done. There's only one function being called. And on Linux we would call fork, because we just set up fork. There's nothing to really pass on, but setup fork gives you a chance to call any function you would like before fork is called. Then fork is called. Afterwards on Linux, we again iterate over all these pointers, and we call setup execve, which gives your objects again a chance to call a function and or to modify the parameters in the execve param structure. And then afterwards, we call execve and pass on the parameters from that structure. So that way, we could support a library user who actually wants to call an additional function between fork and execve. He can just call that function in these handlers, in setup fork, in setup execve, wherever it fits. Do we like this solution? Well, not really. We have to use runtime polymorphism. It's good to use runtime polymorphism if you have to, if you want to, but if you don't need to, if you don't want to, yeah, it's a bit unfortunate to have this base class and having to derive classes from that one. And the other syntax we have seen before with the named parameters look pretty neat. So maybe we can get something which is closer to that one. So another attempt. Now we have our execute function again, and this time it's a variadic template. That means you can pass whatever you like. You can pass as many parameters you like. All the parameters you pass can be based on any type, right? The variadic template doesn't really care about. And then I want to do the same thing again as what I did before. I want to iterate over all these parameters, and I want to call again my setup functions. So all these parameters have a chance to modify the values I will later pass on to create process and execve. So here I use the Boost Fusion library. If you are familiar with Boost Fusion, you know that there are some algorithms which allow you to process heterogeneous containers. So I created here a heterogeneous container, a tuple. A heterogeneous container is a container whose elements have different types. So I take here all the parameters passed on to execute. I call std_make_tuple to put them all together into one container, into a tuple. And then I iterate over all the elements in the tuple with Boost Fusion for each. That way I could really call a function execute like this, that I pass multiple parameters, all separated with a comma. So shell would be one object. So if you think about it, shell is an object. It probably overloads the operator so that I can assign the string dir to it. Then the object is passed to execute. There's another object called stdout, which also overloads an operator. So I can make it look like as if I redirect the output stream to some pipe. So stdout is also passed as a parameter. Shell and stdout can be based on different classes. They only need to be based on a class which provides these setup functions. Here is a possible implementation without a Boost library. I'm not going to talk about this one as we started 10 minutes late. I want to make sure that we are all done in time and you can enjoy the break later. So here's now an implementation where somebody uses the library and wants to call change root. So let's assume that change root, that this is something which is not supported out of the box in Boost process. Yes, you can call execute, that function is provided. You have also a parameter called exe, that is the name of the program you want to execute. So that is all supported out of the box. But now I have a user who wants to change the root directory for that child process. So what can I do now? I can define a new class called changeRootParam. I define the required setup functions. So that is a class I'm only going to use on Linux. So I also will only implement setup fork and setup execv. Then I think about it, where do I need to call the change root function? I need to call it between fork and execve. So setup fork will be called before fork. Setup execve will be called before execve. So that's the place where I need to call change root. And I need to pass in somehow the name of the path to the directory, which I want to be the new root directory. So in this case, I also overload the assignment operator. And when I call the execute function, I can pass on my change root parameter. I can assign a string to it. The string will end up in the dir_member variable and will then be used in the setup execve call to change the root directory. This is how Boost process more or less works as of today. Now let's play a little bit around with this. Let's assume I want to not only redirect the output stream, I want to wait for the child process to exit. So I want execute to return a handle to the child process, and then I want to call a function like wait for exit, and I only want to resume after wait for exit once I know the child process has terminated. So again, we have to think about what are we going to put there, what kind of return type can we use. And as we are using these underlying operating systems functions, we have, of course, to turn to them and have a look at what does actually create process give us, what does fork and execve give us. So if you look at this definition, you don't need to look at it yourself, it's too much text, I know. But there's one parameter at the very end of the long list in create process, which is a process information structure. And this process information thingy has handles to the child process and to the main thread in the child process. It sounds already good, so that is something I can work with. What do I have on Linux? Fork gives me a PID, a process identifier. That is also something I can work with. So I could, for example, create a new class called child. That is now the Linux implementation. Execute will give me an object of type child. Child will contain the PID, that's integer, which fork gives me. And then I can also add a member function called wait for exit. And I can call wait for exit on my child. I get from execute and just wait. Easy. I can do something like this on Windows 2. There I don't work with a PID. Here I work with the process information structure. Again, I can provide a wait for exit member function, and then I call some other Windows functions in order to wait again for the child process to exit. All good. Now we come back to something Bjarne was also talking about today. I think he said a couple of times we don't want to leak resources. So we have to think about what do we put actually in the destructor of child. So when we create a child process and our parent process exits, the child process keeps on running. All good. If we create a child process and the child process exits first, do we need to clean up something? How does it actually work? On Windows, on Linux, you have something like zombies. There are these zombie processes. There are things which have to be cleaned up. On Windows, it's maybe even more obvious when you have, when you just saw the previous slide. We have these handles to the child process and to a thread. And there's a Windows function called close handle. So it implies already that we have to close these handles at some point. So maybe that is something we have to pay attention at. Maybe we have to add something here into the destructor and close the handles when we don't need to access the child process anymore. Now, before I talk now about what we do here in the child destructor and boost process, let's have a quick excursion. Let's imagine the stud vector class in the standard library worked like this. Every time you create a vector and the vector gets destroyed, the destructor of the vector is being called, your program is terminated. You think, what the heck is going on? I mean, who would be so crazy and add a class like this to the standard library? Turns out we have a class like that in the standard library. It's fortunately not vector, it is stud thread. When you create a thread, here when I create a variable t of type stud thread, and the variable t goes out of scope, and I don't do anything else, the destructor of stud thread will terminate my program. A bit weird. So if I don't want my program to be terminated, I need to do something with that thread first. I need, for example, to call join. I need to wait for the thread to terminate. And if I call join, and the thread is terminated, and the program continues, and the variable t is destroyed, then the destructor won't terminate my program anymore. Instead of calling join, I can also call detach. Detach means, okay, I don't care anymore about the thread. The thread can keep on running somewhere else. Just go on with the main thread. And if then the variable t is destroyed, the destructor again won't terminate the program. Now, threads and processes are a bit similar. So what is the reason why the destructor of stud thread by default terminates the program? Could the class not have been designed a bit differently, that we cannot accidentally terminate our program if we don't want to? So let's have a look at a couple of examples why that class is designed the way it is. So here I have a thread which waits for an hour. It doesn't do anything. So after I created this thread, I'm going to throw an exception. Now let's assume that the destructor of stud thread is going to join by default. It's going to wait until that thread has terminated. So what's going to happen? I will throw the exception. The destructor of t is going to be called. If we assume the destructor calls join, it will wait until the thread is done, which means I'm going to wait an hour now until catch sees the exception. It would be a very strange behavior. We would be probably super surprised if we had code like this, where we see, okay, I just threw an exception, but what's the program doing? Why don't I see the exception? Now let's say stud thread would call detach by default in the destructor. What could go wrong? Why doesn't the class do this by default? Now here I have a thread which sleeps for a second, and then it tries to write the number 1 to the variable I, which I pass by reference to the thread. So once I create the thread will wait a bit. Doesn't do anything yet, it will wait a second. After I created the thread, I will throw again an exception. So I will leave the scope. The local variable I is destroyed. It doesn't exist anymore. I will be in the catch clause. Okay, nothing's going to happen there. At the end of the program, I'm going to wait 2 seconds. And while I'm waiting there, the other thread will wake up after a second, and it will try to write 1 to a variable which doesn't exist anymore. Not so good either. So if you think about it, join doesn't really work out, detach doesn't really work out. Maybe we can throw an exception in the destructor. Well, I guess I don't need to explain to you why this is a bad idea. But just to think about it again, let's say the destructor of stud thread throws an exception, and I throw an exception myself. The destructor of thread will throw an exception while there is already an exception being thrown, and the program is terminated again. That doesn't really help us. So we have a couple of alternatives. We could, in the destructor of std_thread, wait by default, but it might slow down exception handling. We might sometimes feel like we are stuck. We threw an exception, we don't see the exception, something's going wrong. We are probably spending hours debugging our program, and then it all comes down to just std_thread waiting forever for a thread to finish. So calling join in the destructor of std_thread isn't really a good alternative. Do nothing by default, meaning calling detach and ignoring the thread, can also screw up our program. We could, for example, access a variable in our thread which doesn't exist anymore because it was living somewhere else, and that scope where it lived before has been exited already. And we can throw an exception. Doesn't work either. So what std_thread does by default, it just terminates your program in the destructor if you don't do anything else with std_thread yourself, explicitly, like calling join or calling detach. Now let's go back to our child class in Boost Process and let's see whether we have similar problems there. What can we do here? Can we just call detach? Can we call join? Can we throw an exception? So this is what we have with std_thread, and let's see what we find in Boost Process child here. So here we have a program where we assume we call wait for exit by default in the destructor. So we are going to start a long running program. Then we are going to throw an exception again. We assume the destructor of child will wait until this other program has exited. And if this other program is a long-running program, we might be again stuck in our exception handling. We might again wait forever until we are in the catch clause. So we have exactly the same problem here as we have with std_thread. Okay, let's try something else. Let's assume we call detach in the destructor of child. Here's an example where I open a text file, then I write 1 to it. Then I start a child process, which should write 2 to the text file. And at the very end of my program, I'm going to write 3 to the text file. So obviously, after I'm done, I expect to find the numbers 1, 2, 3 in that order in my text file. So when I start the child process, I'm going to throw an exception again. And I will assume that the destructor of child calls detach, meaning, okay, I don't care anymore about the child process. Just continue. The child process can keep on running somewhere else. So I assume for my sample program that I didn't mean to throw an exception. I wanted to wait for the child process to exit first. There is this wait for exit call. But if you have a bigger program and you do a lot of other operations between creating a child process and waiting for exit, there's of course a possibility that something throws an exception. So in my program, I throw the exception explicitly, but the idea is that you have a program where you don't explicitly throw an exception. But let's say something goes wrong between execute and wait for exit, an exception is thrown, you leave the scope, and you write 3 to your text file. And if that other program, which has that strange name, writes 2 after 5 seconds to the text file, if it actually writes that number 2 only after 5 seconds, then my program has written 1 and 2 when the other program is going 1 and 3 when the other program is going to write 2. So in this example, when I look at the text file, I will find the numbers 1, 3, 2 in that order. So calling detach in the destructor of child can lead to a problem like this one. It's maybe not as bad as in the case of std_thread because I'm not accessing invalid memory. But then you could also argue it's actually even worse because that is something you are not immediately noticing, that you find a different order of the data in the file. So in the first case with std_thread, probably the program crashes and you know you did something wrong. The other thread program works fine, and yeah, it seems to be all okay. Let's assume we are going to throw an exception in the destructor of child. I know, stupid idea, but let's assume it for now. What can happen? Well, if an exception is thrown explicitly, like I do here with throw 1, and the destructor of child is going to be executed, and that this destructor will throw an exception, then again we have an exception while there's an ongoing exception, our program will be terminated. And that is, of course, the same problem as we have with stud thread. What we could also do, we could, of course, now, just like stud thread, explicitly terminate the program if nobody calls any other function on our child class first, like join or detach. But then we have additional problems here, because when we call terminate in our example where we use a thread, the thread is also automatically terminated. When we call terminate here, our process is terminated, but not necessarily the child process. The child process keeps on running. Now we could argue, okay, then we are not only going to terminate our current process, but also the child process. But let's say you have something like this, where you start 2 child processes. So you get an exception again, then the one destructor of the one child process is executed first. That one will terminate the current process. It will terminate the child process. But then there's this other child process which will keep on running. So it doesn't give us a consistent solution either. So our goal is in the end to guarantee unexpected behavior in all use cases, just like stud thread does. So the solution with stud thread is, okay, I'm just going to terminate everything unless you call join or detach yourself. We can also terminate something in the boost process case, but what exactly are we going to terminate? Especially if you have multiple child processes. What is the guaranteed expected behavior we can offer to you? So the problem with boost process is that we have resources distributed across a lot of processes, while in the stud thread case, everything is in one process. And when that process is terminated, all the resources are cleaned up. We don't have a happy end yet, unfortunately. The solution we have currently in boost process is that the destructor of child calls terminate. It terminates your current process. It doesn't terminate your child processes. So if your current process is terminated, the child process keeps on running. If that is something you're worried about, you would need to somehow manage this yourself. We don't have a happy end yet, but at the same time, it's an invitation for you to share your ideas and contribute to a library like this one. As I said, this is a library which is brand new in Boost. It's now part of the Boost libraries only for 1.5 weeks. And as I said, there are still people working on it, making sure that all these details are that the details are all going to work out in a way as we expected in the Boost community. So if you are a beginner, if you don't know much yet about C++, it's an excellent opportunity to strengthen your software development skills. So you are definitely invited to join the Boost community. If you're not a beginner, if you're an expert and you have ideas how to solve this dilemma, we are happy to hear from you. As I said, I just went through all the alternatives I can think of when it comes to stud thread, but maybe there's a 5th or 6th alternative. And maybe you can actually help us bringing that library to yet another level. As I said, it took us 10 years to get where we are, and that was only possible because there were always people coming in again with new ideas, especially if you have been working on something for too long. You always have the same ideas, and then somebody else comes around and says, hey, did you try this already? And it's then really refreshing to see a brand new idea. So just because you haven't been around for 10 years doesn't mean that you can't help out. So if you know something, talk to me, join the Boost mailing lists, and bring yourself in. Last but not least, even if you don't want to write any code or you have no idea how to improve Boost process, maybe you have other resources available which you can bring in and help us out. After all, we all benefit if an open source community like Boost grows, and everyone is welcome to join us and contribute as much as you want and as much as you can. I'm done with my talk. It was a good timing, so we are not too late. I was already worried that I'm too late after we started 10 minutes late. If you have any questions, that's now your chance. Were you just... Pardon? Oh, okay. Okay. The microphone. The microphone is going around.
hello, thank you for this introduction to your work. When you mention the fact you can't, if there is an exception thrown, you know, you lose the problem with if an exception is thrown and you can't do, yes, this one I think. By default, you wait for the end of the process.
Yeah, this one.
And if an exception is thrown, then you are stuck there. I know, but maybe it's time for a refreshing for me because I'm not sure. I always forgot why it's not a good idea. But in the destructor, you can test if an exception is currently being thrown, and then maybe have a different decision in that situation. And maybe the decision could be also for the other case to kill, for example, the child process only, and not the main process. So I suppose you have talked about that already. Could you share your experience with these approaches?
Yeah, it is definitely something we could do. I don't really have a strong opinion on whether that's the right thing to do or the wrong thing to do. I followed up Boost process for about 8 years, so I haven't been around since 2006 when the first draft was created. I stumbled across this Boost library in 2008. I found it in the Boost sandbox, and it looked pretty complete. That complete that I thought, oh, will take me only a weekend, then the library is done. But that was 8 years ago, and it's only now that the library actually entered the Boost libraries. So every time we turn to the Boost mailing lists and we ask for feedback, I feel like we have the same discussions again and again and again. There are a lot of people who haven't been around before. They don't know what has been discussed before. And then there are new people joining, and they have different experiences. So I'm now very careful saying this is a good idea or this is a bad idea. There are a lot of ideas, and there are a lot of reasons to design the library this way or that way. And we need actually the input from the users to find out what are the ideas everybody wants to see. Yeah. So if everybody says, we don't like the idea that stood terminate is called, we would actually prefer that wait for exit is called, I'm happy with that solution. Yeah.
Hey, in your slides we saw that like those name parameters were discussed in the review, and extensibility for like if someone wants to add chroot or some other things in between, and error handling. Like which other main points did you have in those 10 years during review and during implementation? Like what would you recommend for people to make that shorter? Like if we had to do another library for Boost, how could we make that shorter?
Yeah.
Or which are the main points to discuss there?
Yeah. So you mean now in general or specifically about Boost process when it comes to the design decisions we made in Boost process? In general. Okay. I don't think we have that much time. Yeah. There are, I don't know, you probably follow the Boost mailing list? A bit, yeah. I mean, there are a couple of organizational problems we're trying to deal with in the Boost community. One problem with Boost process has been, for example, that this library was already for 2 years in the review queue until somebody picked it up and it actually went through a review. So I think it entered the review queue in 2014, 2013, and then 2 years nothing happened. And then somebody asked what's actually going on, and then I said, well, take the library out of the review queue again. There's no point in the library waiting for 2 years for a review. And that was the last thing I actually did. That this library is now part of the Boost library is the work of somebody else who took over from me. So I've been with the library for 8 years, and I'm happy that somebody else got interested in the library and went on working on this. So one of the problems we have is we don't have enough people who are looking at the review queues, taking the time to read the documentation of a library, and taking the library through these 10 days of reviews in the community. So that's one of the things we definitely need to work on. I think there are way more libraries stuck in the review queue. The Boost process went now through it, but I think there are a lot of other developers who would be happy if somebody helped them out and tells them, okay, you have been waiting for a long time, let's have a look, can we maybe review that library in the community and see where that can enter Boost. It doesn't have much to do with the design decisions in the library, but it's one of the organizational problems we have to solve in the community.
So you're using name parameters, and there is a library in Boost, if I remember correctly, for doing this specifically. Are you using that library to implement the name parameters pattern, or are you doing it ad hoc?
Yeah, indeed. There's a library called Boost Parameter. It's another Boost library you can use to define named parameters. We are not using that library because in our case, our named parameters need to provide these member functions like setup, create process, setup, and so on. And that is something you cannot really do with Boost Parameter. So yes, you can have named parameters, but you don't have the rest of it what we need for Boost process. So yeah, good question, but no, we are not using Boost parameters for Boost process.
Hey, thanks for the talk. In the first example, you have a pipe, a process, etc. On the, I might think of some reason, but what was the main reason you didn't have, the API with, for example, like an overloading of the binary or operator, instead of the pipe, for example, or this kind of syntax actually?
You're wondering why the syntax looks like this?
Yeah, for example, we could imagine like to overload the, instead of the std out and then greater than p. I mean, we could basically remove the make pipe to the pipe with just basically operator overloading of like the binary or this. I mean, this kind of syntax.
Yeah.
In order to have really like a shell kind of syntax, but in C++. I mean,
there have been proposals to introduce a domain-specific language in Boost process so that you can use more or less the same syntax you're used to from the command line. But we have been so busy for 10 years just to get this done that we always told the other guys who wanted to introduce something more domain-specific, let's build this on top of that. So this redirection from standard out to the pipe is something Clemens added recently. Clemens is the guy who is now maintaining that library and who went through the review. So when I worked on it, I had a lot of name parameters like shell, and another one like bind stood out, and then you could assign a pipe to bind stood out. So I was just using the assignment operators, not any other operators. So that is something indeed one could work on in the future and add more.
Do you have a clever solution for passing arguments to the program that's executed?
Yes, there are also name parameters which you can use to forward arguments to the program, to the child process. That is something which is supported out of the box, and I think it looks more or less like as you would expect. So you can, for example, pass a vector of strings, which would then be forwarded as the parameters to the child process. So the documentation of Boost process has a list of all the named parameters being supported.
Is there a way to pass parameters dependent on runtime information? For instance, when I want to bind std out dependent on runtime config, I would have to write execute for multiple times. So is there a way to do that?
Yeah, good question. I don't know whether we have a way in Boost process right now. I know that there are always discussions on the mailing list when the interface of execute comes up. There are always the folks who want to do things at runtime, and then the other folks come in and say, no, we don't want to do these things at runtime. We want to do these things at compile time. So you always switch between the interfaces, but hopefully there's a way to support both sides. What the library does right now as of today, I don't know. But if you're on the Boost mailing list, or if you would like to join the Boost mailing list, that is the feedback we need. So as I said, the library is now in Boost, but it doesn't mean that the library is perfect or that we are already done. It was good to get the library in Boost, because I'm afraid if that library would have been another 10 years somewhere outside of Boost on GitHub, we would just forget over time all the experience we gathered in the past 10 years. So as the library is in Boost now, and as it will be shipped with all the other Boost libraries, hopefully there will be more people using that library, hopefully there will be more feedback, and hopefully all of us helps us to improve the library much faster than having to wait yet another 10 years for the next step.
last one.
And I think we are done. And you can enjoy your break and coffee and cake. Thanks.